Hello, everybody, and welcome to Advent of Code again. Look at that. We got people tuning in, even for the early hours. It's excited to have you here. I'm glad that you managed to stumble across this, whether that's via the tweets, via the Blue Sky, via the Kotlin Lang Slack, and you did not miss our early session. A lot of familiar faces here who've probably heard this message a whole bunch of times. Maybe also a couple of new folks. It's a great way for us to also maybe cover a different time zone for some folks. How's everybody doing today? How was the puzzle? Did something throw you for a loop? Did everything go as expected? I have to admit, today was kind of odd. Because, quite frankly, the problem itself, first of all, it's a very interesting problem to think about. But what I found out in discussing with my guest today is that there are fundamentally different ways of how you can solve it, which is a delight. And additionally, some assumptions that you might have about performance might hold, might not hold, which is always so curious. So we'll definitely see some things, and of course, we will. Well, it's maybe not of course, but we might even see just a little bit of visualization, even with today's puzzle, which, when you think about it, I don't think it lends itself so much to being visualized. Today I had fun. That's excellent. Wanted to use a sequence and needed a way to calculate a single combination given an index. Interesting. Miguel thinks that it would have been way harder. Well, yeah. I mean, sometimes the big worries that you get is whether you're gonna, whether if you build a brute force solution, whether that's still gonna work in part 2 or not. I am very curious about the idea that you're mentioning here, Sax and Tosh. I'm not gonna throw it up on screen just yet because that seems pretty similar to what I might be showing later on. That's very interesting. Next level bit bashing to get the combos bitwise even in part 2. Oh, I'm liking this. Let me know for a second here if you used recursion in today's problem. I am quite curious. Because you can solve it with recursion. You can also solve it without recursion. Jury's still out on which solution I prefer. Jury's still out on which solution you might prefer. Yeah, look at that. Recursion before breakfast? Maybe. I tried not to be obsessed with the runtime, but then I spent way too long to bring the time down to less than 20 milliseconds. That is fun. That's very exciting. And I'll be honest with you, I feel like there's a certain type of puzzle that just inspires this because, again, I don't think I'm particularly concerned myself with runtimes usually this year. But this problem just kind of lent itself to checking whether there's maybe some more assumptions you can cram in, or maybe you can change something about the algorithm. Okay, we had some recursion. We had someone do a manual stack. Very interesting. Maya says recursion often breaks my brain, which is also totally valid. Yeah, when the recursion for the win. It sounds like today's problem is gonna be quite curious. But of course, I do want to just very briefly remind you about the overall situation that you find yourself in, which is Advent of Code, an event that is sponsored by JetBrains, which is quite a delight. And of course, I want to send you just one last time. Well, not one last time. It's like those TV shows where they say now is the last chance to get something for a special price, and then it just happens to be for another 5 hours. No, of course not. But still more streams all the way until day 12. I want you to be aware of all the cool things that you can do to win prizes, which is you can join one of our leaderboards and compete for a top spot. Or you can join one of our leaderboards and just hang out and solve a couple of problems, which is also more than enough. Or if you don't even want to be in a leaderboard, you can just tag your repository using the AOC 2024 in Kotlin topic, which you can just add. And as long as we have a way of contacting you and you've solved a couple of problems using Kotlin, then you are already eligible to win some prizes potentially. That's quite exciting. And of course, I want to invite you to try something new. Try a different way of solving a problem. Try approaching it using maybe a different paradigm than you're typically used to. You know, Kotlin is a multi-paradigm language. So you get to do all of those things. Yeah. Apart from that, I think there's not much else to talk about. I will give a brief disclaimer about why our stream is earlier today. A little behind the scenes look. JetBrains has our Christmas party later this afternoon. And I don't want to miss that. I love Advent of Code, but I'm not going to miss some good food and some nice hangouts with some of my colleagues. But for now, I'm very excited to still hang out with somebody who has over the years kind of now also become I want to say a staple, definitely recurring and most welcome guest for Advent of Code in Kotlin. And that is Olaf Gottschalk. Hey, Olaf, welcome to the show.
Hi, Sebastian. Hi. Thanks for inviting me.
Yeah. How are you doing?
I'm doing fine. Thanks.
I am.
This is a very, very, very different situation than all the years before. It's bright. It's not that Christmassy. It's so early.
I do apologize for that, but you know, sometimes you gotta work around real life just a little bit.
That's true.
I am so glad to have you back. I'm also so glad to see you in your new setup here. I think we need to remove the screen for a second here and take a closer look at this. I mean, yeah. First of all, you're looking sharp. You're looking like well lit, both from the natural light we still have, but also with that wonderful little fireplace in the background.
That's
what
cool.
A delight!
Thanks.
Yeah, it's really good to have you back. You are typically known for kind of being the visualizer guy. You've contributed a lot of visualizations for our previous streams, which of course we are still very much thankful for. And I mean, I think we can just start with that question on today's problem, which is do we have a visualization for today?
We have a little secret thing we can show in the end. That's what I could tell our viewers already. But it's not the kind of visualization that I did the years before. So I was really unfortunate. This morning when I opened the puzzle, I was like, oh, dang, this doesn't look like a graph or anything that I could animate. So I was kind of a little bit disappointed about the puzzle. But, well, that's the way it is in Advent of Code. You never know what you get.
Yep, it's very much hit or miss when it comes to visualizability.
Yes.
But yeah, let's actually maybe just dive right in and see what today's puzzle is so that we get a better understanding and our brain cells can start working. And of course, you don't want to miss those secret things that might be happening at the end, so do stick around and learn something new. I'm gonna throw my screen back on here, and of course, the reading hat goes back on. It is time for our dramatic reading of Advent of Code 2024 Day 7, Bridge Repair. The historians take you to a familiar rope bridge over a river in the middle of a jungle. The chief isn't on this side of the bridge, though. Maybe he's on the other side? When you go to cross the bridge, you notice a group of engineers trying to repair it. Apparently, it breaks pretty frequently. You won't be able to cross until it's fixed. You ask how long it'll take. The engineers tell you that it only needs final calibrations, but some young elephants were playing nearby and stole all the operators from their calibration equations. They could finish the calibrations if only someone could determine which test values could possibly be produced by placing any combination of operators into their calibration equations, your puzzle input. For example, 190, 10, 19, 3,267, 81, 40, 27, 83, 17, 5. Each line represents a single equation. The test value appears before the colon on each line. It is your job to determine whether the remaining numbers can be combined with operators to produce the test value. Operators are always evaluated left to right, not according to precedence rules. Furthermore, numbers in the equations cannot be rearranged. Glancing into the jungle, you can see elephants holding two different types of operators: add, plus, and multiply, star. Only 3 of the above equations can be made true by inserting operators. 190, 10, 19 has only one position that accepts an operator, between 10 and 19. Choosing plus would give 29, but choosing times would give the test value 10 times 19 equals 190. 3,267, 81, 40, 27, has 2 positions for operators. Of the 4 possible configurations of the operators, 2 cause the right side to match the test value. 81 plus 40 times 27 and 81 times 40 plus 27. Both equal 3,267 when evaluated left to right. 292, 11, 6, 16, 20 can be solved in exactly one way. 11 plus 6 times 16 plus 20. The engineers just need the total calibration result, which is the sum of the test values from just the equations that could possibly be true. In the above example, the sum of the test values for the 3 equations listed above is 3,749. Determine which equations could possibly be true. What is their total calibration result? All right, Olaf, besides thinking, oof, this one's going to be a little toughy to visualize, what went through your head when you read a part of this description?
So first of all, when I read such a story in Advent of Code, I have the feeling like, okay, what is the trick today? Do I have to care about big numbers or deep recursions that make me throw off everything and don't get to the result quickly? So I really, even at day 7, I expected something to be very, very tricky. The Chinese remainder theme where you have to do modulo arithmetics and stuff like that. So this is really the kind of puzzle where I immediately know nothing to visualize and some number thing that could give a problem.
Mm-hmm. And looking at the input, these are pretty big numbers at times.
Yes. That was also the very first thought I had. Like, how big do the numbers get? What is the data type that we should use to tackle all of these problems that we are going to face? Correct.
Okay, cool. Should we just jump right into your code then, and we'll take it from there?
Yes, we can do that. Definitely.
Let's do that. So we are connected. We're connected together here using. Whoops! I think I just lost that connection for a second. All right, I'm just gonna reconnect us for a split second here. And in the meantime, we can try and stare a little bit at this
The
input.
numbers.
Yeah, and we can figure out some things, which is that at least at first glance, I'm not seeing any negative numbers.
Yes, that's cool. But
That's
also you have,
interesting. Yeah.
we know that the big numbers in front. So I really have a problem with detecting whether that fits into a long value by just looking at it. So even though I do a lot with numbers, or let's say I do a lot with Kotlin and programming, I still can't see some number exceeding long just by looking at it. So when I see these long numbers, I go like, they might not fit into a long value. But surprisingly, maybe that's a spoiler, they do.
That is pretty interesting. The other part that I noticed immediately was that the numbers over here are rather small-ish. They're like typically, they are, I think, only 3 digits max. And these lines don't get particularly long either. Like, you maybe get like a dozen, maybe like 12 or so. I've dropped you a new invite link. Great, wonderful.
Yes.
So you are back. And we are just going to jump straight back into your, I suppose, your day 7. So
yes, but maybe we should start with day in the morning.
Okay,
are you following me?
Yes, I am following you.
Because due to the massive cleanup and bettering of my problems this morning, it would be kind of hard, or not hard. It would be kind of giving away the fun if we look at the final solution. Because I have to admit, because of these things that I had to think about this morning, remember, I have my alarm set at 5:45 in the morning. So I get my first coffee, I get to the reading part of the puzzle, and it really got me afraid in the very beginning. And whenever I read something like that, my initial urge is be safe, use data types that are not blowing away, and don't go for recursion immediately because I really fear stack overflows and stuff like that. So I'm really afraid of doing a recursion in Advent of Code, only to see that it takes too long and blows up my stack. So what I did this morning, and I can walk you a little bit through this. I mean, we have had many puzzles this year that start out with giving away that you have to sum some numbers that are like the result of filtering the lines. That's the first thing. We have to sum the values of the matching equations that we can fix. So you see, using these functional ways to do that is a very easy start. You have to filter for some predicate, and then you build the sum of the first number. Maybe it's worth looking at my very first step here. So longtime viewers of this video series know I got my own setup. So my project is kind of large. You just saw that when you downloaded it. Because I want to be as quick as possible. And I have to say, that's not always giving me the advantage over people that do everything by hand. I have my library. And every year it happens again that I forgot my own functions. And so there is a learning curve every December to get back on track. But this first line here really tells my setup. You see my day classes are always like derived from an abstract class day. And this one hides away the reading part of the puzzle. So I have these input things. Input is a value that gives me a puzzle input type. And the puzzle input type has functions like mapping, or give me the lines, or give me the sections. So even puzzles that are like 2 sections or 3 sections of input, I can quickly type input.section1, input.section2, stuff like that. And here you see a convenience function for every line, extract all long numbers. So we have seen the puzzle. Every line consists of a first value, which is the test value, and then the values of the equation. But this function here, it doesn't care about the separation at all. It uses regular expressions to pass anything that resembles a number, and it then converts them to long. But, and this is also my first safety net, this function then checks whether it fits in long. So if you use the extract all ints, it will tell you with a warning, hey, there are numbers that don't go into int. Yeah, that's the cool part about this. So I knew immediately I had to go for long values. One thing less to worry about. But as you see here, I didn't even though this one gives me the safety that there are no bigger numbers in the input, how could I know that summing up my result doesn't blow long? So this was my safety net to say I'm doing the sum in big integer world.
Yeah, and more probably more scarily now that we've looked at the input, multiplying up all of the individual values. That does sound like it's going to give you a big number.
Yes, correct. So there is, of course, other things that I try to avoid there. But let's have a look at how do we do the test equation. As I said, being so afraid of doing a direct recursive approach, in my head, when I have two operations and I have like n spaces to put in operations of either being add or multiply, I know it's a binary number and I have to just, so my brute force attack, that's one thing again. I did not dare to think about, is it possible to optimize this or do I have to test every combination? And I immediately said I have to test every combination. Let's hope that it does do this in time. And you see here, and again, I'm showing you the very dirty code. I would never commit into a project anywhere. So you see using O for operations, operators, basically. See, using O in real life code is really bad, operators. And you see here my logic. So if you want to have every combination of bits turned on and off, and you know that you need that many, so let's walk through this, a quick thing. So given the line, this is the input line from our initial puzzle input, and because I didn't spend time to separate the test value from the original values, you see that the test value is directly derived from this list of long numbers and converted to a big integer. The first one is then the first operand, and the rest or remaining is drop the first two that I have put into these two values. So I'm just basically having the test value, the first value, and all the coming values. And because if we have one more, in the first example we had just two numbers, we have one first and one remaining, you see that we need to have one operator only. And doing the math, if you look at this is the bit shift operation, where you basically say, take the number 1 and shift it as many times to the left as we need operands, in this case, 1 time. So we stay at 1. And that's basically all we want here. We have this this 4-0 in 0 to whatever that is. Yeah. So we have one more, so we have 1, and that's it. So what do we do here? Actually, that might be a problem here. I'm not really sure. Should have been maybe... no, you have to shift 1 less than the size. And you see here the Kotlin operator, because I started out with until -1, like this. Yeah? And then it told me, hey, you can use the operator that says up to below that value. So long story short, we are now having the operators in O as a binary number where every bit denotes whether I want to add or multiply. And at that time, of course, I didn't have any expectation on what to come there, so I just wrote on. What do? We take the first value, again, big integer, my fear to overblow. Because of the multiplications, I had like this thought, better to go safe in this case. And I have a variable too big, because I thought, of course, I don't want to search for the rest if I already have a number that is too big. Having a number that is too big and then adding more operations, because we knew adding and multiplication will always produce bigger or equal numbers. So adding 0 or multiplying by 1. So if I have a number that is too big, I can stop immediately and know this is not a solution. So what do we do here? This is the inner for loop that basically goes through my operators. So for every remaining operand, I need one operator. If the value I'm currently building, it's a variable here, is already bigger than the test value, we break out and set the flag, hey, we exceeded the limit already. So out of this loop. And then this was my big, like, just do it quick and dirty. So looking at the operator's bit mask it by the index and pick out the bit that denotes what do I do at this position in my math. Yeah. Maybe something like this. If you have a comment, A, B, see, so we have two operators here. This one would be the bit that is either 0 or 1 for saying multiply or add, and this one is 0 or 1. Yeah. And then you see here, try addition. I just said if it's bigger than 0, that's an addition. If it's 0, it's multiplication. That was just, you just need two states, so it doesn't matter which one you take.
Yep.
So, and then you say if we do addition, we do v plus equals, and if we do multiplication, v times equals. So increasing the value of v. And we do that for every operand that we have. And once we're done, or we fell out of the loop because we exceeded the limit, we basically say, okay, if the value is now the test value, that's a match. Otherwise, we quit and say we didn't find any match. So again, this inner loop here tries this outer loop tries every combination. And if you found the very first combination that makes the number fit, we know it's a true and we exit this. That's how it works, basically. And I've heard that you have a similar solution, right?
I actually do. We can jump into that for just a second here, because I think the key. So the key understanding that was required for me to write my solution was, well, I need to be able to understand that I have, whenever I look at the numbers, right, there are spaces that I need to fill with operators, and I have two types of operators, which means I can model this just like you did as a binary number, right? And then interpret 0 to be like a plus and 1 to be a times operator, which is pretty much the exact same thing. So how did I do this? I decided, okay, we first of all, we just generate a binary number. So we figure out how many operand slots we have. That's operands.size -1. You know, if you're sleepy in the morning, you can confirm this by assuming you have 5 fingers. You have 1, 2, 3, 4 empty spaces. That's one less space. So you know that you have 4 slots between 5 elements, or just -1 slots for an arbitrary size. And then the question is, how many combinations do you have? And anybody who, learned this 2, 4, 8, 16, 32, whatever, quickly knows that those bits are just powers of 2. So you have 2 to the number of slots possible combinations. And
actually, this is exactly what I did with the shift left operation. Just that this involves the power function now. So.
Yes, that's I think that's an interesting speed optimization that we should talk about a little bit in as well. But yeah, so here you can see that the overall structure of the code, I think, is very similar, right? We're still doing the 2 loops here. We first of all grab ourselves the initial value as our result, and then we just go over all the indexes that we might be able to put an operand in. We already have our starter value, and then we figure out what the next operand is, where we want to put an operator in between. And the way that I figured out which operator to take for a given loop is pretty much exactly the same. You find your operator combination that I pre-calculated, or that comes from this outer loop. I shift it right, and I and it together with OX1. So there's just a bit mask, so it's the only value. And then I can just say, well, if the operation happens to be 0, then we'll add things. So we can just replace that part. And if the operation is 1, we multiply things.
It's exactly like I did it. Yeah.
Yeah. In the initial solution, I did not. I didn't even break out early. I was just like, we'll just we'll think about that later. We'll just see if it runs. And this is actually one of the parts that I do want to emphasize. for this part. We'll talk about a couple of the other variations later. Really, one of the first things I did, besides these print statements, this is actually what I did this morning. I checked what is the maximum number of operands that I have, which is 12 for my input. And then I just quickly, using like the calculator in like my shortcuts app, I was like, okay, 2 to the 12. And I was like, okay, for part 2, right now it's plus and multiply. So the obvious next step would be there's also like a divide and minus. So I was like, okay, let's see how big 4 to the 12 is, which is like 16 million. I'm like, even if I'm doing a bunch of like crazy operations, I can do 16 million operations like easy, even for the input size. So I was like, okay, I'm not leading myself into a path of like, this isn't even going to work for part 1. And then I just wanted to also make sure that we have zeros as operands, because that might do a little bit of funkiness. If you do a multiply with 0, all of a sudden your numbers get much smaller than they used to before. And with negative numbers as well, like flipping back and forth. Like I eyeballed it before, but I was like, let's be sure that nothing is snuck in there. But yeah, apart from that, my solution is pretty much the exact same one that we already showed. The only difference is that a lot of the like variables for me are just like, they were given a name, so I suppose I could just like hit the inline here a couple of times and probably replace this with something else. But once we do that, all of a sudden the entire thing becomes a lot more golfed.
Yeah.
And looks a lot closer to. Yeah, looks a lot smarter as well all of a sudden, because things no longer have names.
Yeah.
So now you need to use the brain cells to figure out what's
you
going on.
need to understand what you're doing now. Well,
exactly.
don't we want that? I mean, don't tell me you typed your comments in the morning.
This part I did. Because
wow.
I oftentimes just forget what I wanted to do.
Okay, that's nice.
Like oftentimes I'm just like, I'll sketch this out. I'm like, okay, what do we want to do? And then I just stare at my own problem description or like my own breakdown and write it down.
Okay.
So that part does. That part's real.
That's great.
Okay, back to you.
Yeah, nice. Okay, you can follow me again, I guess.
I am.
Yeah. So, just a spoiler here, what I had this morning, for example, breaking out early. You just said you didn't do it. You wanted to see whether you need it. In my first thing, I had like an equal sign here. And if you follow the problem, you might spot where the problem is if you do that. You go out with the number is already too big, but the equal sign, well, there's actually the problem. There could be a 0 that you add or a 1 that you multiply. And because the test data didn't have that, I had my first wrong submission, really because of that equal sign. That was really tough. And AOC is always when you are stressed in the morning and you get your first submission rejected, then hell breaks loose. Especially if you have a date with a JetBrains video in the afternoon, you go like, oh no, please, don't screw me today, please. So, as I said, being especially nervous about the problem and the presentation today, I was like, oh no, please don't tell me I have to do some weird remainder thing now. No, but the problem was just that equal sign. Very easy to fix. I'm not too sure, Seb, whether we should really go into the cleaner version now, because the cleaner version will reveal everything that is in part 2. We could basically go to part 2 and have both together. I mean,
that's do
all
that.
we can say for part 1.
Actually, yes. Actually, I think maybe, I mean, depending on what your solution looks like, maybe it would even be interesting to first look at my solution, and then come back to yes. what you have. Because I think that might make for a better story here. So let's do that. I'm excited. Cool. We're heading back to day 7, part 2. The engineers seem concerned. The total calibration result you gave them is nowhere close to being within safety tolerances. Just then you spot your mistake. Some well-hidden elephants are holding a third type of operator. The concatenation operator, pipe, combines the digits from its left and right inputs into a single number. For example, 12,345 would become 12,345. All operators are still evaluated left to right. Now, apart from the 3 equations that could be made true using only addition and multiplication, the above example has 3 more equations that can be made true by inserting operators. 156, 15, 6 can be made true through a single concatenation. 15 and 6 is 156. 7290 with 6, 8, 6, and 15 can be made true using 6 times 8 concatenate 6 times 15. 192, 17, 8, 14 can be made true using 17 concatenate 8 plus 14. Adding up all 6 test values, the 3 that could be made before using only plus and times, plus the new 3 that can now be made by also using concatenate, produces the new total calibration result of 11,387. Using your new knowledge of elephant hiding spots, determine which equations could possibly be true. What is their total calibration result? So, at this point, I'm actually just going to tell you what I was thinking when I saw this, which is that's one too many states for a binary number.
Spot on.
Yeah.
I also saw, I knew something was coming like that. I mean, everybody has a suspicion that there might be more operators, but still, I had the same thing like, damn, now my binary state is not that easy to go to a ternary state.
But then I remembered something about the wonderful Kotlin language that we have, which is that if you have a number, you can call
toString base.
toString
with a radix.
Which regularly gives you just the number. You can also do that in binary, which gives you the binary number exactly. So this is it radix or is it base? I'm not quite sure.
I think it's radix. I'm not sure.
What the name is? Yeah, it's radix. And of course, this also works with specifying a different type of radix, like 3. So I'm like, you know what I'm gonna do? I'm just gonna take my solution that I have, and instead of working with binary numbers, we're gonna work with ternary numbers. I know everybody loves the ternary operator. I'm not sure how we feel about ternary numbers. Yeah, so
but that's a very, very clever solution, I must say.
This was kind of the approach. And I was like, I'm not, like, again, I was like, I'm a little too sleepy to figure out any kind of math that doesn't involve strings. But again, like, I know how to, like, parse a string, then pick out some elements. So, if we take a look here, we can take a look at my isValid2, which is, again, the version that I wrote this morning. And, you know, I made some smaller changes to it since. But you will see that a lot of the code looks very similar, except now the possible combinations are 3 to the power of operand slots rather than 2, because we have 3 types of operations. All of the regular calculation parts, those haven't really changed. The part that did change was how we get the number. So rather than doing all of this funky bit shifting that we did beforehand with operator combination shift right index and an and, all I do now is I create myself the string, and then I grab myself from essentially walking through it from the back, from the last index. I offset it by my current iteration, and that allows me to essentially traverse the bit string in the same way as, or sorry, I guess now it's not the bit string. I don't know what the ternary version would be. I'm not gonna say that.
It's the digits. It's the digit string.
Yes,
I would say
exactly. So the digit string, I iterate kind of from the back the same way as the shift operator would do, and now I just get 3 values back. It's either a 0, a 1, or a 2. They happen to be characters,
cool.
but of course could be converted. And since I'm already in string land, there's not much left to do here. I might as well just also turn both my calculation and my new thing into strings and literally string concatenate them. Throw that out, runs for maybe 6 seconds or so, and gets you a solution. Like, it's fine. This works.
It's nice. You can also optimize this very quickly by pulling out the operator combination to string outside the loop, because you don't have to do that for every operand. You can do it just once.
That's very true. That is a very easy optimization. You're totally right.
Yeah.
That probably saves me a whole bunch of time, potentially.
Potentially, yeah.
And I mean, while we still have this in context, maybe it also makes sense to talk about what I wanted to do next, because I kind of I didn't quite enjoy the fact that I did have strings in here. I was like, this does seem like a hack. Because we're still just working with numbers. They just happen to be in a different base. And I should be able to work with this. So I wrote a stringless variant, well, a mainly stringless variant, which just replicates the same logic, but this time without using any kind of strings. Essentially, all that we had to do was creating a bit shift operation that, instead of shifting individual bits, would shift in base 3, which really is just however far you want to shift. It's dividing by 3. We can quickly check that makes sense for us, because a right shift on individual bits, again on like 1s and 0s, if you shift to the right, that's equivalent to a division by 2 in base 2. So here we do the same thing. Might be quite interesting to figure out or to talk a little bit later about the performance implications here, because I tried doing this first using math.pow for the powers to just get that same number rather than just doing a repeat. That turned out to be quite slow, interestingly enough. But that's we'll talk a little bit more about performance implication in a little bit. This right here is the equivalent of the bit mask. So rather than just doing like an AND operator, we just make sure that we get the remainder of of a division by 3, which again is our base. So it just gives us, like, conceptually the last digit. And then once we've done that, we can actually just do our 3 operations that are now numbers again. We can also
How much faster?
How much faster? Let's have a quick look. I do have some data down here. I have my baseline, which takes about 6 seconds, and then going totally stringless, which is one more optimization, gets me down to 4 seconds. But this is still even with me not even doing this early exit that we did beforehand. So this you can see that this does not have a check for whether we are larger than our result. We're still trying all of the combinations. But yeah, there was just one string left in this, so I decided I was gonna go totally stringless, which is it's the exact same implementation here. The only change now is, once again, we're doing like the concatenation is now calculated by offsetting base. First of all, determining the number of digits that are in our new operand, which you do by doing log 10 and then +1. I did Google that, but it did help. And then essentially just once again now in base 10 doing a bunch of left shifts. So just moving the digits that we have over to the left. So calc res, everything we have so far, we move it over to the left, and then adding in that freely created space of just a bunch of zeros, we're adding our new value. And yeah, so this was kind of like then the new baseline that also has now has this break in here. The combination of adding that little break there, like this early exit, shaves off a cool 3 point, like almost a second. Not quite, but almost, which is, quite significant. And then I did my patented move of throwing the entire thing into a run blocking and starting an async block using Kotlin coroutines. So actually using the 12 cores that my machine has, and running all of these combinations in parallel, which bumps the time down to 500 milliseconds. And that's as far as I've gotten. I'm sure there's more potential to optimize, but that's how far I got. Woo.
That's cool.
Yeah, I'll be honest with you, I'm quite happy with this one.
I got a slight hint for you for your next elegant move of going in parallel mode. So I'm a big fan of the Arrow library, and it has just been bumped to the next version 2.0.0, so the next major release. And for stuff like this, it has a very, very handy par map function. So you have a map anywhere, you say par map, and that's it. Given you have a suspend function, you can say par map, and it does it in parallel with everything dealt for you. You don't have to worry about it. It's very cool. It can even work on flows now with par map unordered. So in these cases, like, it doesn't matter which order, you can even use par map unordered, and it will do even better.
Very cool. Speaking of, by the way, I did have one question that I almost forgot to ask you, because when we were talking about things, you mentioned that essentially you want to try all combinations of all the operators, right? Did you and your giant library of things that you're pulling along with you? I'm just gonna briefly show your Gradle file that has well, it's not that many, but you bring in a couple of libraries. Does none of them have like a cool function to just do like all combinations given a set? Because when I'm just poking over here into the Rust world for a second, Rust has in iter tools, they have combinations, which allows you to iterate through all k-length combinations in an iterator, which is, it's kind of what we want, right? Like, we have a collection of plus and times, and we just want to have all combinations given the length of like how many slots we have. Yes.
So no, I don't have a library that I depend on that brings this kind of math. I find it quite hard to find good libraries out of the JVM world, actually. So whenever in the later days of Advent of Code, there are some Pythoneers that can really pull one library and then do everything with one call. That's really a shame for the Java world that there are so many things missing. But in my own tool set, I have some functions that do stuff like that. So I have helper functions. You can go into the utils that I have here. And you see circular list is one of those. Just open the utils and you see that I have combinatorics and compositions. And in there you have exactly these things, combinations of whatever, and it's all written by my own here, given some sources. Of course, I didn't invent this. It's like just in Kotlin the way to do this. But as I said, it's early in the month, and it's been 1 year since I've used these functions. So I felt very insecure this morning pulling them out of that toolbox. So I hope I get more chances to learn my own library again.
Oh, that's so exciting. Yeah, no, I was just curious, because it feels like, for me, I every time I start Advent of Code, so far I've always been going in with an empty project entirely, which it does not put me at an advantage. Let's put it that way. But so I was just curious if maybe something here would have provided some wonderful help, or if you would have had some recommendations. I believe that maybe Guava from the JVM world maybe has something for that. Could
be. I never checked.
Yeah. So apparently, Google Common Collect Set Combinations has. So apparently, this one has combinations, which gives you the set of all subsets of set of size. Which, first of all, that's a great sentence to say. So I guess Guava might be worth a look. I haven't looked into it myself.
Yeah.
Okay. Yeah. But so this is the overall. My solution was just, what if base 2 was base 3 instead, and what if we could do that without ducking around with strings, which would be great.
Nice.
So back to you.
Yeah. Let's wait a second more to talk about the elephant in the room by looking at my quick and dirty morning solution. How did I go from binary to ternary? And this is really funny. It's like, first of all, you see part 2 is here, and it's the same function. I just quickly put test equation 2. So I really show you what I did do in the morning. So test equation 2 is not refactored by any means. So I would never leave it like this. I just honestly show you what I did this morning. So when you see what I did is, this took me more time than I should have taken for that. Given the solution is so close, and we will come to that in just a second, I wrote a helper function. You know, I'm a big fan of sequences and sequence builders. And whenever I know that there is a large number of combinations, I know that I cannot use lists, or basically I would say I don't want to use lists whenever I know it's a big, huge thing. And in this case and many others, if you do know it's a throwaway thing, like you want to iterate over something, it's like only, it's not data, it can be created out of an algorithm. You should always go for sequences to spare the memory load. You don't need the array allocation and everything on the heap. Basically completely useless. You wait for the heap to be allocated, filled with the data, and then you iterate over it. Take a sequence and job is done. So here's a sequence I wrote, count with. So it's, again, no comments, so not good code. The receiver of this function is the alphabet. So what numbers or things do we count with? I had in mind that you can count with A, B, and C as an alphabet, or 1, 2, 3, or add, multiply, concat. So the generic type T is the alphabet. No, it's the base type of the alphabet. The list of T is basically the alphabet. So everything that I can count with. And here I denote I need a certain size. In this case, it's how many operators I need. And the result is a sequence of one exact combination, counting up. That's what the sequence does. How do you do such things? This is very, very basic. Like, go into a sequence builder. And remember, the cool thing about sequence builders is really, now you can write your code with loops and whatever you want. And whenever there is a new value, you basically yield that value, and this is what the sequence spills out to the receiving side that uses the sequence for anything. So you see here inside I say, okay, given my alphabet and an initial value, which I now initialize to being the 0th element of the alphabet, so basically everything is 0 of the given size. I calculate the next value in a loop. So I'm turning my internal thing into a mutable list. That's the thing that actually counts. And then I go into my loop and yield this first element, making sure I don't expose my mutability. So always to list, to not give anybody the chance to screw up the thing from the outside world. And here you see how we count. How do we count? We start at the right end. I'm counting like a human would count. I could have done this the other way, of course. It doesn't matter for this thing. Starting at the most right digit, down to the first digit, also the 0th. We just look at what do we have at this position currently. And if we are not yet at the last alphabet that we have, we just increase that one and we are done. If we are at the last alphabet character, we need to wrap around and carry over. And the carry over is done. Okay, we set this to 0th element. We go back to the 0. And the loop makes sure that we try to increase the next digit. So that's what this one does. And it's a sequence. And given that you now have a sequence, you basically, in your algorithm, you can do this. You say, given this alphabet of 0, 1, 2, add, multiply, concat. With that many operands, we do take every combination of that, and this is the same code that we had before. We just already know that the ops is a list of ints denoting whether you have to add, multiply, or concat. You have a question, I guess.
Yes, I do. Hold on. Here's what I would like to do for a second. Right-click, split right.
Ah, cool.
Because now I was quite curious. I think you have now created. It's not permutations. I guess you've genericized your int range dot combinations.
Yes.
Which previously was the same thing.
Correct.
But just on an int range, like on a list of integers.
I could have used it. Yeah. You hit my weak spot, Seb. It's exactly my weak spot that I don't remember my own library function in the morning, and I write it myself. And later, when I refactor, I realize, actually, it's a very sad story. If you look at my times, I took way too much time between part 1 and part 2 because, drum roll, I took the wrong function. I took permutations, not realizing that the permutations doesn't include all of the different orderings. So I was missing some. And that took me like a few minutes to realize, no, that's not the right function. And then I wrote it myself. That's what I did this morning.
Okay. Yeah, fair enough. But I just, because I was just curious. It's such a, again, what I think is so fun about this is, I mean, by the way, to everybody who's already mentioning a recursive solution, relax. We're getting there as well. But
don't talk about the elephant.
I'm just making sure people don't lose their minds. No, it's all good. No, it's just so curious to me because the problem itself. So like even in part 2 here, it hasn't been super difficult to solve, but I feel like there has been so many aspects that are worth discussing about this, from like just from the approaches and from how you can interpret it and so on, which actually makes me really enjoy this problem.
Cool. Shall we open the box now and go for the better way to do it?
Let's go for it. Well, I mean, that's to be discussed, but sure. Yes. I'll follow you, and you can try to sell me on,
I will try
your
to
next solution.
So everybody has seen what a hassle it can be to do all of this in the morning and to find the right solution here. And I haven't even talked about the nice things that Kotlin brings you, like the zipping of the operator with the operand and stuff like that. This is all stuff very, very nice. But once you're done with this, you really have to answer the question, is the algorithm I'm using here really the best approach for this puzzle? And remember, in the beginning, you dissected the puzzle input, and you saw, and I can open this now myself, I guess, you saw very, very clearly that the number of operands is not that big. We really don't have that big of a list of operands, not thousands or 10,000s, whatever. It's all countable. And so how do you approach such a problem when you are like not that sleepy and not that afraid of a not working recursive solution? Well, you do a recursive solution. That's what you do when you don't want to do it differently. So how does it look? Let's switch to my day 7 final result. And this looks so different. It has nothing to do with what we did before. And probably we will have to go into how does it solve this thing a little bit more in detail. I'm trying to, look at the part 1 and part 2. Because the two things are so easy, you see on a high level now with cleaned up code. Part 1 says, solve my puzzle using add and multiply. And part 2 says, solve my puzzle using add, multiply, and concat. And for the curious, now, what did I do here to make this speaking? Well, we're using a sealed interface operator here, which basically provides us with a long and long combination to a long value. By the way, this has all been scaled down by me to going to long values once I checked that everything, my results, everything didn't blow the long range. So I threw away my big integer solution. But this approach here, of course, would work exactly the same if you used big integer. If the numbers were larger, you could still do it like this. So why do we use a sealed interface? Because now we can use these nice little data objects to each implement the function for add, which basically takes the two values, adds them, the multiply takes them and multiplies them, and the concat. So here we see the most naive approach of concat. We'll talk about this later. Given the two AB values, put them into a string and interpret it back to a long value. That's the concatenation.
I have a question here,
Yes.
or a comment, I think. Because I think this line is a little wilder than what it might actually look like. Because what you're specifying here is you're specifying an interface that inherits from a function type.
Yes.
Like this, you're saying anything that implements this interface called operator needs to fundamentally act like a function that takes two longs and returns a long, which happens
Correct.
to be done by using the invoke operator.
Yes.
I am curious now, is it the same if we were to instead just specify an operator from invoke with
It's the same.
So both of these work the same,
Yes.
right? There's no
Yes.
no body, but
Well,
yeah.
there might be intricate differences that I don't know of, but on the JVM level, it's the same. I actually tried functional interfaces. So now we could look at Kotlin language design, because I think in many, many ways, Kotlin is so cool because you don't have to type that many boilerplate stuff. But actually, when I wrote this, I was like, I don't want to override fun invoke all the time. I just want to give you this lambda somewhere. And you can do such things with functional interfaces. If I declared this interface a fun interface with only one function, I can create instances with the object type, just saying object or curly braces, and it all boils down to writing a lambda and saying this is my implementation of the functional interface. But I found out this morning that the combination of sealed interface and fun interface is not supported. If you type sealed fun interface, you exactly see this. And this, doesn't work. So you are not allowed to do this.
Well, that's interesting.
Yeah, I learned this morning. I mean, you have to think about it. What does it mean? What I wanted to have as an effect, I wanted to spare boilerplate code in the declaration. Yeah. So you have to think about how could the language somehow I need to give the lambda to the declaration of the data object, and that's not that easy.
Okay, but hold on. I don't think, I mean, maybe you'll prove me wrong later on, but I don't think you do anything in your code that actually requires this to be a sealed hierarchy, no?
No, it doesn't have to be. Definitely not.
So you could also have just used a fun interface here by itself,
Probably.
And you would have most likely saved yourself a little bit of boiler code. But then, of course, if at a later point somehow you do want to make sure that your when statement does indeed cover all the operators, which, that might happen in real code, then you might still want to have a sealed hierarchy. So I still agree This is a trade-off.
Yes. So you already said some things about how to use these things. I mean, I'm using a sealed interface. It felt like natural to me. We know all of the operations that we have, so it's sealed. Technically, the when statement, if you use a when statement anywhere, that would be safe to use with a sealed interface without any else. But in this case, because it's also implementing the functional interface here, I actually don't use a when. I just call the operation on its invoke. So that's why it works. Yeah. And
yes. We'll get back to the problem. But I do have to ask, and this it's very much a matter of taste. Do you find this easier to read than this?
I do. Personally,
okay.
I do. Yes.
That is very interesting to me, because for me this feels fundamentally easier to understand.
I like one-liners,
Yeah, sure, I get that. But what I like about this version is that it clearly specifies. First of all, you can give your function names. I actually don't know if you can do that.
You can do the same here
in the type signature. Wow.
Yes.
No,
you can.
No, you can't.
But you can give it in some other places, not here.
Yes,
sorry.
You can give it for like lambda parameters, I'm pretty sure, for functions. Yes. But in this one, my logic for this is the following. If I'm giving this code to somebody who does not know about like inheriting from a function type, these 3 lines spell out exactly like how you would know how to work with this, because it's just an interface that happens to have a function that you can implement. And yeah, the calling convention changes a little bit, but like technically you can still just use .invoke, even though nobody does that. Like that is still possible. That's why I personally kind of vibe with this solution a little bit more. But now I think now that we've discussed both, we can just move back to your solution, because now everybody knows what's happening under the hood. Okay.
One more thought to what you just said. If I would go for the 3 lines of specifying everything in plain words, I would argue somebody who is not familiar with the functional types would also struggle with operator fun invoke. If I go that way, I would say it's a normal function apply or do it or work or what process. I would use my own function name because that clearly everybody who's ever done anything with an interface should know. Because the fun invoke operator, so I'm not sure whether everybody would immediately know what an operator function by name invoke is.
Correct. However, my point standing here is the following. Just to briefly make this note: if I have a function and I have an implementation of my operator, so if I have a data object mul, I don't know, which happens to be my operator 2, how do I implement it? Well, I implement that member. That part doesn't matter. Invoke can just do a plus b and print it. My point is that if I happen to now have a mul, I can still call invoke. This is still a function that I can see has been written, and I can still call it as invoke. And then, of course, you're just getting into the territory of naming things. Anyway, this was a wonderful little sidetrack. I can see that people in Twitch, which, by the way, hi, we're also streaming on Twitch, are also having opinions on this and the arguments. But yeah, this was I very much enjoyed this little sidetrack. Cool. We're somewhere on the way on towards a solution, I think.
Yes, let's go for the recursion now, because this is like it's a long drum roll today to go for the actual algorithm. So we have seen the 3 operations as they are declared now. How does this solving now work and now it's really getting short. You've seen that to take you back here, solve using these operators is the only difference between the 2 parts is what operators are at your hand. What could you use? Like this one was hidden in the forest by the elephant. So how do you solve the lines using the given operators? Especially when I'm typing this, I like var args because it looks so neat to say solve it using ABC. That's really something handy to type. But then once you have a var arg, you sometimes have to deal with this being an array under the hood. But you'll see that. So what do? Remember, we have to take all of the equations and filter by the ones that could be solved. And once we have filtered, we sum the very first value. That's coming from our solutions that we discussed before. But this here now deviates a little bit. So I'm taking the line. The line is the raw line coming from the puzzle input, being the test value at the first position and having the operands. Everything after that is just the operands that I have. And here we go. We have a function test equation. The test value is the value we should achieve. And here, this could have been done differently, but let's look at this. I start with my value 0. That's my starting value. And I hand in my operands coming from the puzzle input. And here you see how to pass on the operators as a list to the next function. And the next function is called test equation. And here we hit our long awaited solution. This is done in a recursive way. How do you do this? Well, think about it. If I gave you only one number, so if our input line, we can scroll down to the demo input here. If the input line would be just 42:42, life would be very, very easy, wouldn't it? It would either be a line that is doable and matches, or it wouldn't if it's like that. But there is no place for any operations here. So this is the goal we are striving for. And this is how the recursive solution actually works. Given the test value and the accumulated value that we have so far, and given the remaining operands that we have to add or multiply or concat, with these possible operators, we now have to do the very logic things. I really love when it's done and works. I love to see how recursion is readable. Like if the operand is empty, so there is no operand left, all we have to do is the current value we have the test value, and we return our end result, true or false. That's the goal we are striving for. If the value we have is already bigger than the test value, that's our exit. Remember the exit out of the loop? If we have already accumulated a value that is larger than the test value, we can immediately say, nope, that's not a solution here. And now for any other situation, we are not exceeding the value yet, and we have operands left. So what do? We pick the next operand from our list by using first. We can use first safely because we have made sure here it's not empty. Otherwise, I always say use first or null to be really sure that you don't crash. And the remaining operands for our next iteration into the recursion is the operands, but we can drop the first one. That's the one we actually picked. Now, when I write code like this, I often would like to see Kotlin having destructuring with putting the rest into a list, like saying in one line, next, comma, remaining. That's not possible in Kotlin. Yep. So you have to do 2 lines for that.
You would like to have a split that does head and tail for the list, I guess.
Yeah.
And you're telling, okay, hold on. You're telling me that if I search for head in your library, I'm not gonna find a head function? That seems like something you should have. I actually can't find anything. Interesting.
I can tell you why I don't have this myself, because it's in the arrow library. You can use non-empty lists with arrow, and you have a head and a tail. I could have used that. Yes. So basically, we know that, well, technically, here the operands is empty. We could have done this. Operands to non-empty list or null. So this is the safe way to go to a non-empty list. And then if it's null, we can return to test value equals value. So this line is exactly doing the same as this line. These 2 lines are doing the same. I see on the stream that sometimes my cursor icon hides what I'm doing. So this is the non-empty list of operand. And if I do that, of course, I can say non-empty list of operands head. That's the first. And this is the non-empty list NEL operands. And then there should be a tail.
And can you also destructure it?
I think they don't have a destructure, but it's easy to write as your own function. So coming from the Kotlin standard library and using regexes sometimes, if they had a destructured method, you can just use that or write it your own. Yeah.
Okay. All right.
That's another sidetrack we can enter, but that takes way too long now. I mean, it's a 5-minute thing.
No worries. Let me just check if there's. Okay, this just gives you 2 elements. Okay. Yep.
Yeah. Cool. Let's go back to the code. I hope I can redo it. Yeah. So the quick and easy way.
Can I just say that's actually quite impressive? Because you made a bunch of changes, I made a bunch of changes, I undid some of my changes, and then you undid both mine and your changes to end up in a solid state again. That's pretty cool. Yeah,
it works. Okay, so how do we work with this now? So this is the trick now, and I like these functions, as I told many times. We have operators given that we can try out. And all we do now is, the question with recursion is, we have now set up the stage for trying the next operator on whatever we have left. And to do that, we iterate over any operator we are allowed to use. So I might call this operator, because the type is operator. It's better, I guess. So what we do is we call our self-test equation with the test value. That stays the same for every recursion call. And here, this is the invoke. So for everybody who's not that familiar with this, basically I'm calling the invoke method here with value and next of my operator, and the remaining operands and the list of operators that are staying the same. The cool thing is this any function, again, is a short circuit one. It's basically doing a loop over the values, and for the very first that makes this one go to true, so the predicate is true, the result is going to be true without going any further. It's basically exactly what you want. So,
That's
and
smooth.
and I must honestly say, I mean, this is a lot of setup to do it like really, really nice. But looking at this code for the real thing, that's so much shorter and more elegant than trying our bit shifts and ternary things. So after I had this solution, I was like, okay, I need more coffee tomorrow to really come to that.
Very, very nice. I do see from a lot of people here some suggestions for performance.
Yes. We also have some in stock, remember?
Yeah, we sure do.
Let's see what we have. I can't read the stream. I'm just looking at your window here. So read what we have as questions.
Okay. Let me grab one here. There's a whole bunch of comments. So some folks doing it the clever way gets it down to 90 milliseconds. I mean, first of all, maybe it's interesting to know how long your solution runs with the test equation compared to what I have. I'm not sure if you have a quick way to measure this.
I have a more elaborate way to measure this, because we have discussed that we can look at the performance aspects. And so I can show you something here. What I prepared, basically.
Because a lot of people say that like the recursive solution is the fastest.
Yes. And I can spoil less than 2 seconds, definitely. I think on my machine, I'm like 90 to 100 milliseconds with the most performance optimized version. So what I did is here, I have, so first things first, what ways do we have to make this faster? We discussed before we had the stream, Seb, that maybe the concatenation. So let's look at the concat operation. The concat operation we have here, it basically puts the two long numbers into a string, and then it converts it back to a long number. And clearly, when you think about it, a long number is something in a modern CPU that's easy to handle for any addition, multiplication. It's very, very, very fast. And a string, it's a char array. Yeah, you have to do conversions. It must be slow. So my first thought was like, these three operations, they clearly differ in speed, because those are really fast and this one is comparatively slow. But how slow is it? You should always measure and not guess. How do I measure? So I did, and here you see my library used. So the thought we had now is, if concat is the slowest operation, and think about the recursion. So in recursion, we pick one operator for the very first spot, and then we go into recursion. So we fix the first operator should be an add, and then go on with the remaining operators. What if we pick the fast ones first? So search in the land of the faster operations first, and only in the end go to the slower ones, presumably slower ones. And so I did the following. Given our three operations, and here you see my library, and please give me all of the permutations. So reorder them in every possible order. We try to now, with the ordered, to measure the time. So for measuring the time, what I did is very easy Kotlin fast approach, not going into specific profilers. So I know this is not on a very fine-grained level. I'm using 100 repetitions, measure the time it takes to solve using this ordering, and print out the time it took. So in order to see that, all I have to do is basically add something here, profile order, just call that, and let's see. I hope this works. Yes, it seems to work. So now it takes a little bit more time to do 100 sets of this order, and it runs on your machine, I guess?
It does.
Okay, let's see how fast it is.
See here, we're getting that core all the way satiated.
If this is too long for the stream, we can go down in the number of iterations.
How many iterations?
100.
I mean,
it's way faster here, so I'm really surprised it didn't come out with a result now. But let's go for for 10.
Sure.
And try it again.
Okay.
So compared to my machine, this is really slow, Seb. What's going on?
Oh, I'm sorry. I guess I don't have the M4 Mac with, and I guess I'm also doing screen sharing and some other things. But you know.
So you have to take this with a big grain of salt, because 10 repetitions is not really a lot.
Okay, but you also have some actual numbers as well from your machine, right?
Yes. So basically what you see here is, if you look at the slowest here is, it's totally different than what I did before on my machine. So the point is not really clear. On my machine, it was clear that the concat first, the 516, 558 was slower than the rest. So I got what I wanted to look for. Concat is too slow. Okay, so we take this as a result that we did a priori. We just take this as a given. So how can we make this operation faster? That was our question. And it's really interesting to dive into this one here. And I have prepared something. So, and some of that came from your idea. So we can define an operation concat stringless, because now we have this hierarchy, we can just add more operations. And this is the mathematical way to approach this. You basically calculate how many digits does the B number have. And with this knowledge, you say shift in terms of our decimal system, shift A by the number of digits of B to the left, 10 times power of digits, and then add B. Yep. So basically what we do here in Stringland can be done here in Mathland by just doing the math. Yeah, and you can measure that, which I think we must not do now, because probably won't show you what I want. Yeah, and this is one version, and this was faster already. But it turned out, and this is a fun fact, so for everybody who's into how the machines work, all of these methods here, the log10 and the power methods, they all are done on double or floating point numbers. I mean, this one is a function from Kotlin, but you see internally it goes to double, because power logarithms and stuff like that on the machine level is always done with floating point arithmetic. And this is actually surprisingly slow compared to what you can do with a long number. So I have another version, and that is the final one that took me under the 100 milliseconds. I'll show it to you here. Let's make this a con2. So it's getting longer, but sometimes you are doing this trade-off. What you can do actually to always do anything in long is you can first check whether the B value is below 10, because then it's easy to say A times 10 plus B, all in long. And here, remember this code, you've seen something very, very similar in your code before.
Yep.
You are doing the, in one loop, you're basically both shifting A by always one decimal digit to the left, while dividing B in effect counting how many digits B has by constantly dividing it by 10 until it is 0. And doing this is really the fastest way to do this. Yeah.
Very nice. No, that's awesome. This is a really cool way of solving this. Yeah, this was like one of the observations that really did astound me a little bit. You can see this like ever so slightly in like some of my sketches. You can see that like I had this where I decided to emulate my bit shift operation by dividing by 3. Right, you can literally see like in the comments, I used to do this using like first by figuring out by how much to divide by with math.pow, but then realized that this one is like it's significantly faster to do an operation that does not do like a 2 double conversion and then brings that back into an integer. Which was like the impact was surprising to me that was that much.
Yeah, it is very really measurable, definitely measurable. I mean, we are talking milliseconds now, but still measurable, at least on my machine without the streaming stuff. Yeah, so that's definitely a thing. Do you think we can show the last bit of surprise things that we discussed?
I think so. I think we've because we've been here for a minute. This has been actually quite a long stream. So of course, everybody who stayed around, we appreciate them extra hard in this early hour, no less. So yeah, let's see it.
Okay, so we discussed that I'm always keen to do any kind of visualization. But here I was really like, no, I can't really do an animation for that. I was thinking about stuff I could do, but to no avail. So, but there is one thing you can do if you want to visualize how the recursion actually works. And I got one thing in my tool set that I can use in this situation. And it's called GraphViz. GraphViz is a library that allows you to generate directed and non-directed graphs by using a language. And in this particular case, by using Java or Kotlin functions to define how the graph looks like. So what do we do? Basically, if you want to visualize anything and you have a running solution, I basically always copy my code into a separate file, and then I go the hacky way to get any kind of visualization. And what I did basically is in the test equation recursion function, I added this graph stuff. And you see here we have mutable graphs and mutable nodes. This comes from the GraphViz library, and it basically is the basis to declare graph nodes with links between the graph nodes. So taking my former test equation recursion function, you add some lines here in the exit cases. So remember, this was the fast exit when it's either a match or it's too big or too slow. And here we have exceeded the possible test value already. So I always use the return false and add an also here. Return blah, 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 and add also do this. This is the quick and easy way to put something to it. Mm-hmm. And if you run this now, so basically what you can do, go to my main function. You can put in your numbers here. So this is out of the puzzle demo data, one of the demo things, where there is like 3 numbers. And if you run this, it generates the graph using GraphViz. And it puts the graph result into a PNG file that you can now see. I'm not sure. It doesn't. Does it follow you? No, it doesn't. Okay, that's it.
But I have it right here.
Cool. Now this is a boring one, but I haven't had the time to really try out more. But we can walk through this as well. So given the line that says 3,267, we have the numbers 81, 40, and 27 with no operators in between. We are going into the first call, and we are starting with the value 0, which is my base value, and we put plus as the first try to solve this puzzle. So this is the first level of recursion, and we have the remaining numbers 40, 27. We can then see that it now goes down and adds another plus here in the 81 plus 40. This is because I start with my value 0. Even that value 0 is combined with the rest using plus. And then you see 81 plus 40 is 121. And then we try out either adding 27 or multiplying by 27. And one is too small and one is a match. That's how it works. And you can plug in all of the numbers, but sadly, if you take anything from the real input, this graph gets so big that GraphViz says, I can't render this anymore. So you can only play around with small numbers. But it's there, and you can test it out now and plug in things.
Very nice. And of course, I will also be sharing the link to your repo where all of this is living in the chat so that people have an opportunity of trying this stuff by themselves.
Yes. Yeah, that's cool.
Wow. Wow, Olaf, we've done a lot today. Again, I sometimes when I solve the puzzle in the morning, I'm like, I wonder what we're going to chat about. And then, these things, they just kind of spiral out of control a little bit.
That's true. Yeah. Sadly, no new features of Kotlin 2.1. I wanted to have some when statements with conditions, but no, sadly not today.
That's fine. But maybe we'll get some new things tomorrow, where, of course, we will have another stream. Then, once again, at the regular hours. So make sure if you don't want to miss that, head on over to our streams page on YouTube and hit that little notify me button for the remainder of the streams. We are going to be streaming all the way until day 12, and there's a whole lot of cool guests that you should not miss. So yeah, make sure you stop by. Tomorrow is going to be quite interesting because we're going to be looking at a problem in Kotlin, and maybe even beyond that. We'll see what that looks like. Should be a fun time either way. So yeah, thank you so much, Olaf, for coming on. Really appreciate it. It's always good to have you. And I think I've learned a little bit myself here. Certainly about how other people feel about inheriting from functional types, but also just seeing a really nice solution and a really cool approach to fixing these things. So thank you, and thank you to everybody at home who decided to tune in. We will see you in a future episode, and take care. Have a lovely Saturday. Bye-bye.
Bye-bye.